Hello everyone, this is Dhanlakshmi, Assistant Professor from Tricky Department of R&D Engineering College. In this session, I would like to discuss about the single-phase semi-converter, where in this previous session we discussed about single-phase full converter. So in this semi-converter, we can find the difference that it's a single-phase semi-converter, or otherwise it is called a single-phase half-controlled converter. The name comes that because out of 4 devices, as we know that in full converter, we're going to use 4 switches. If all the 4 switches are controlled devices, then we say that as a full converter. If the number of if the half the number of devices are controlled and half the number of devices are uncontrolled, then we say that as a half controlled converter. The other name of half control converter is our semi converter. So here you can see that out of 4 switches, that is in the earlier case in the single phase full converter, we were having 4 switches, 4 thyristors T1, T2, T3, T4. Whereas in case of semi converter, here you can see that the 2 are thyristors and the other 2 are diodes. That is half out of 4, half the number 2 are controlled and 2 are uncontrolled. So that's why we say this as a half controlled converter. The other name is semi converter. And whenever we go for semi-converter, we were also using, we're going to connect a freewheeling diode across the load just to provide the freewheeling path for the inductor to release its energy, to extinguish out its energy. So here we can see the discussion, we can see the operation of single phase semi-converter. As already discussed, here you can see this single phase semi-converter should convert the AC bidirectional quantity into unidirectional at the load side. And as we know that during positive half cycle, thyristors T1 and D1, right? T1, D1 are going to conduct, and during negative half cycle, thyristors T2 and D2 are going to conduct. So here we can see the waveform here. So as you see here, once again, if we take the pen. So here you can see that. So as we know that during positive half cycle, the polarity of the supply will be positive here. So the polarity, you can see that the polarity of the supply will be positive, and here the polarity of the supply will be negative during positive half cycle. So when the positive half cycle comes, the thyristors T1 and T1 is forward bias, and therefore the conduction will be from the source to thyristor T1 and to the load, and then back to D1, and it will return to the supply. So this is how the conduction of flow will conduction or the current flow will be. So that's you can see that the current is flowing from the current is flowing in the load from top to bottom. That is from R to this way, this direction. So here you can see during this period, that is during positive half cycle. During our positive half cycle, the thyristor P1 and diode D1 are going to conduct up to pi. Right, and this is alpha. The alpha is the triggering angle, or the alpha is called as delay angle. The delay, once the gate is triggered, from the instant alpha, there will be a conduction. Right, and here you can see that. So during the next, that is from alpha to pi plus alpha. This is the instant. This instant is pi. So up to pi, the positive half cycle, or at the pi, the positive half cycle gets over. So here we can see that from pi to the next half cycle will be starting from pi plus alpha, right? So this pi plus alpha, where it is going to trigger our thyristor T2. So during this period, right, that is from pi to pi plus alpha. During this period is what called as a freewheeling period, right? Because during this freewheeling period, the inductor, what this inductor will do, inductor will release all its energy through this freewheeling diode. So this freewheeling diode is creating a path for it, is creating a freewheeling path for the inductor to release its energy. So therefore, when the freewheeling diode is conducting, which means that this freewheeling diode is a shorted now, right? And as we know that the voltage across the shorted path is zero. So if the voltage across this freewheeling diode is zero, then the load voltage should also be zero. So that's why during this period, during this freewheeling period, the voltage becomes zero. During this freewheeling period, the voltage becomes zero. So this is happening because during this period, the freewheeling diode, when it conducts, it becomes shorted. So and in a short circuited path, the voltage is zero. Parallel to that, since it is parallel to the load, the voltage across the load will also be zero. From 0 to alpha, then from alpha to pi, then from pi to pi plus alpha. So here we can see that from alpha to pi. So from alpha to pi, there is a you can see that from alpha to pi, the current flow will be from the source to the thyristor T1 and load and back to D1. So during this period, thyristor T1 and D1 will be conducting, and it is just following your input source voltage. So right, then from pi to pi plus alpha, where the energy stored in the inductor has to be released. So a freewheeling path is created here. You can see that the inductor is releasing its energy through this freewheeling diode. It freewheels its energy. So during this period, the voltage is zero. The output voltage, the load voltage is zero. Why? Because when the freewheeling diode is conducting, which means that this path is, or one second, I need to take okay, so here you can see that when the freewheeling diode is conducting, which means that that path or that path is the voltage, that path is short circuited, and we know that that path is short circuited, and we know that the voltage in a shorted path is zero. Since this freewheeling diode is in parallel with the load, the voltage in the load is also zero. So during freewheeling action, the voltage will be zero. That is what we need to understand here. So during positive half cycle, thyristor T1 and D1 will be conducting up to pi. So right, then from pi to pi plus alpha, the next triggering period of the next thyristor T2, during this period, the freewheeling action will be taking place. And as the freewheeling action is taking place, since the freewheeling diode is going to freewheel its energy, freewheel the inductor energy. So this freewheeling diode, when it is conducting, which means that this path is shorter, that when, as we know that in a shorter path, the voltage is zero, that makes the load voltage should also be zero, because in parallel, the voltages are same. So during freewheeling action, the voltage will be zero, output voltage will be zero, right? And from pi alpha, that is from pi plus alpha to 2 pi, right? That is from pi plus alpha, that is sorry. From pi plus alpha to 2 pi, the negative half cycle conducts, that is the negative half cycle will be delivered, and during the negative half cycle, the thyristor T2 and D2 will be conducting. So during negative half cycle, thyristor T2 and D2 will be conducting. So here you can see that during negative half cycle, the polarity has been changed here. So here it becomes negative and here it becomes positive. So down the current flow is from supply, from the positive of the, that is from this end of the supply to the thyristor T2, then load, and then back to D2. Right? So therefore you can see that it is converting that negative cycle into, or that is it has been, the negative half cycles have been rectified into positive. And the semiconductor, and the single phase semiconductor, we have two configuration. One is symmetrical, the other one is asymmetrical. So here we have in the configuration, we can have two types. One is symmetrical, the other one is asymmetrical. When we have one thyristor and one diode in a leg, if a leg carries one thyristor and one diode, we say that configuration is a symmetrical configuration. And the other case, that is the legs are symmetrical. Why we say this configuration is symmetrical? Because the legs are symmetrical. Both the legs are symmetrical, which is carrying one thyristor and one diode. Whereas in case of this asymmetrical configuration, here you can see that that is. Yeah, here you can see that in both the, whether it is in a single leg itself, that is one leg is going to carry both the thyristors, whereas the other leg is going to carry both the diodes, right? So where the legs are asymmetrical here, right? So that's why we say this type of configuration as an asymmetrical semiconductor, right? So in symmetrical configuration, that if the legs are symmetrical, which is going to carry one thyristor and one diode, then we say that configuration is symmetrical converter. Whereas in case of asymmetrical converter, where one leg will be conducting both the thyristor, other leg will be conducting both diodes, which makes the legs to be asymmetrical. That's why we say this configuration as our asymmetrical configuration. Yes.